Hi, we start with this video the first part of the course, which is dedicated to curves in construction and architecture. We begin by remembering some of the curves already known by everyone, curves that will appear along with many others throughout the course. There are many ways of describing plane curves. The simplest one is probably as a graph of a continuous function of real variable given in its explicit form in Cartesian coordinates. We can describe many plane curves in that way. The first example are straight lines, as the one you have on the screen. Another of the most well-known curves for its geometric properties is the parabola. Here we see its definition as the graph of a given function explicitly. The sign of the parameter a indicates to where the parabola opens. In this image now, you see several examples. It might be also useful to describe the variable x as a function of y. That is, x equals a function g of y. Geometrically, it can be seen as a rotation. In the case of the parabolas, now they open to the left and to the right. Parabolas have been widely used in architecture for its beauty, as those in Park Güell, Barcelona, designed by the architect Antoni Gaudí. There are many other examples, for example in bridges and other constructions. We can generalize the previous situation considering the curves that are composed by the points of the plane satisfying certain condition. That condition between x and y defines an implicit function. Formally, we will have an equation f of x and y equals c, where c is a constant and f is certain continuous function of two variables. The most trivial example is again the line. Another curve that can be considered in this way is the circle, that is, the set of all points of the plane at equal distance r to a point called the center. If the center has coordinates x0, y0, then the implicit equation is the one you have at the bottom of the screen. We will recall later that this curve is not the graph of a function of one variable. With this approach, we can also have a look at the parabola. The parabola is the locus of points of the plane equidistant from a given point called focus and a given line called directrix. One can find analytically the relationship between the vertex and the equations with the focus and the directrix, but we will not do it here. In the case where the directrix is vertical, the points must satisfy the equation of this type at the bottom of the screen. Or the ellipse, defined as the set of the points of the plane satisfying that the sum of the distances to two fixed points, called foci, is constant. The relation between the parameters a and b of the equation and the ellipse can be also found here. In architecture, we find, for example, the Mormon Tabernacle of Salt Lake City in the state of Utah, United States. Its form of ellipsoid takes advantage of the properties of the ellipse to have very good acoustics. Another curve appearing in this context is the hyperbola. This consists of the set of points such that the difference in absolute value of the distances to 2 points, the foci, is constant. Although we have already mentioned it, we insist on the fact that the graph of a continuous function is always a curve, but a curve is not necessarily a graph of a function. This fact is clearly seen in the case of the circle. If we think of it as the graph of some function f, any value of x other than r or minus r would give two values of y. This is not the graph of a function, but the union of the graph of two different functions. And the same would happen if we consider x as a function of y. In mathematical terms, a curve is the locus of the successive positions of a point with respect to a degree of freedom. Or equivalently, the set of the points, the coordinates of which with respect to a reference system are continuous functions of a parameter. For example, a circle is a trajectory that would follow a moving point A by making a complete turn around a point C at a fixed distance r. We will learn in later videos how to describe this movement according to a parameter. This will be very convenient for a later study of many properties and applications of curves. This example illustrates very well the fact that a curve is not the same as the path describing it. For example, the previous moving object can give 2 complete turns around the point. The path could be the same, but would correspond to a different curve, as it passes twice for each point. We will now see some known examples of curves in three-dimensional space, such as intersections of surfaces. For instance, the intersection of 2 non-parallel planes provide a line in R3. As in the case of plane curves, space curves can be described as the movement of an object in the space. For example, this is the case of a linear motion, the line, or this movement climbing a cylinder while spinning around it at a constant rate. This describes the so-called helix. Examples of helices can be also found in Parkwell in Barcelona. But many curves are handled much better when x and y are given in terms of a third variable, which may be, for example, the time elapsed since the beginning of the movement. Furthermore, there are many others, as for example spirals or the lemniscate, both on a screen, that have an easier description when using a new system of coordinates called polar coordinates. We will see this in another video of the course. Finally, we show here a beautiful curve that could be impossible to deal with the techniques we have seen in this video. For this, it will be essential to introduce the concept of parametrization.